All right, I hope you're comfortable and ready to drift off. Tonight, we're going to try something a little different to help you get there. This is a Terrors of Space iceberg, and it's designed to give your mind something vast and fascinating to wander with as you fall asleep. Now, don't let the name worry you. The terrors we'll talk about aren't meant to be scary in a way that keeps you awake. They're ideas so big and so profound that they can make our own daily worries feel very small and very distant. It's a journey into awe, and hopefully, a journey into deep rest. The way this works is simple. We'll start at the top of the iceberg with ideas you might have heard of before. Then, as we go on, we'll sink deeper and deeper into the more strange, obscure, and mind-bending concepts. You don't need to follow every detail. Just let the ideas float by. So, let's begin our descent. The tip of the iceberg. First up is the most obvious one: simple exposure to the vacuum. It's the baseline problem of space. Our bodies are perfectly built for living under the immense weight and pressure of Earth's atmosphere. If you take that away, the results are instantaneous. The air in your lungs would be pulled out, and the moisture on your tongue and in your eyes would instantly boil away in the near-zero pressure. It's a fundamental reminder that we are creatures of Earth. Every astronaut in a spacesuit is just wearing their own personal, tiny bubble of our world's environment. And tied directly to the vacuum is the problem of extreme temperatures. This is one of those things that's hard to wrap your head around. Here on Earth, our atmosphere is like a gentle buffer. It spreads the sun's heat around during the day and holds on to it like a blanket during the night. In space, there's no blanket, so you get these brutal, instantaneous temperature swings. If you're on a spacewalk and the sun is shining on you, the surface of your suit can heat up to over 120 degrees Celsius, which is well above boiling. But the moment you float into a shadow, with no air to hold any heat, the temperature plummets instantly to something like minus 160 Celsius. The only thing keeping an astronaut alive is a system of water-cooling tubes, like a personal radiator, constantly working to keep their body at a stable temperature. Next on our list is something our own star sends our way: solar flares. I think of the sun as having a personality. Most of the time it's calm and life-giving, but it has a temper. The surface of the sun is this chaotic tangle of magnetic fields, and sometimes those fields snap and reconnect, releasing a colossal amount of energy. This is a solar flare, a huge burst of X-rays and other radiation that travels out at the speed of light. Our atmosphere protects us from them completely, but an astronaut on a spacewalk would be very exposed. A big enough flare could be a serious radiation event, so they have to constantly monitor the sun's weather. This leads to a related and maybe more troublesome phenomenon: coronal mass ejections, or CMEs. This is when a flare also throws out a huge cloud of actual stuff, billions of tons of magnetized plasma from the sun's atmosphere.
If that cloud hits a spacecraft, it can fry its electronics and is another big radiation risk for the crew.
Now, let's talk about the physical stuff floating around out there. The problem of micrometeoroids and space debris. The vacuum of space isn't perfectly empty. It's filled with tiny particles. Some are natural, little grains of dust from comets and asteroids called micrometeoroids. Others are things we've left behind. Every mission, every satellite launch leaves a little bit of junk. Flecks of paint, discarded bolts, frozen droplets of fuel. Now, a fleck of paint doesn't sound very scary, but when it's traveling at 28,000 kilometers per hour, that's about 10 times faster than a rifle bullet. It has incredible kinetic energy. A tiny paint chip can hit with the force of a bowling ball. That's why spacesuits and spacecraft have to be built with multiple layers of shielding, like a form of space-age armor, designed to break up these tiny projectiles before they can puncture something vital. It's a constant, low-level game of chance. And after a mission is all said and done, there's still one last fiery hurdle to overcome: re-entry. Coming home is one of the most dangerous parts of any spaceflight. A capsule returning from orbit is traveling at immense speed. When it hits the upper layers of our atmosphere, the air in front of it can't move out of the way fast enough, so it gets compressed. And when you compress a gas that much, it gets incredibly hot. This creates a sheath of superheated plasma around the capsule, with temperatures hotter than the surface of the sun. The capsule has to be protected by a special heat shield that is designed to ablate or burn away, carrying the intense heat with it. It's a beautiful but incredibly precise process of turning speed into fire and plasma, just to slow down enough to gently parachute home.
All right, let's take a breath and sink a little deeper beneath the surface of the water. We are now moving into the next layer of the iceberg. Layer 2, below the surface. First up is a danger that, to me, is much more unsettling than a solar flare because you can't hide from it. It's called galactic cosmic rays, or GCRs. Solar flares are like sudden, intense radiation storms. GCRs are like a constant, quiet, penetrating drizzle that is always there. These are the hearts of atoms, iron nuclei, protons, that were thrown out of supernova explosions millions of years ago in distant parts of the galaxy. They've been traveling across space ever since, accelerated to nearly the speed of light. They are so energetic that they don't really get stopped by the metal hull of a spaceship. They just zip right through it, and right through an astronaut's body. As they pass through, they can break strands of DNA and damage cells. Astronauts on the space station have even reported seeing strange flashes of light in their eyes, even when they are closed. It's thought that this is the physical sensation of a single GCR particle passing through their retina or optic nerve. It's a direct, physical reminder that you are floating in a universe filled with invisible high-energy bullets. Over a long mission, this constant exposure adds up, increasing the long-term health risks for the crew. It's the universe's quiet toll
for traveling between the stars.
The next one on this layer is a problem we created ourselves, a kind of slow-motion crisis happening right above our heads. It's the Kessler syndrome. We talked about space debris, all the little bits of junk we have in orbit. The Kessler syndrome is the theoretical tipping point for that problem. The idea was proposed by a NASA scientist named Donald Kessler back in the 70s. He realized that as we put more and more satellites into orbit, the chance of a collision goes up. Here's the scary part. If two satellites were to accidentally crash into each other, that single event could create thousands of new pieces of debris. Each of those new fragments would then be its own projectile, capable of hitting another satellite, which would then create even more debris. This could set off a cascading chain reaction, a self-sustaining wave of collisions that would rapidly pollute an entire orbital shell with a swarm of fast-moving shrapnel. If that were to happen in a crucial orbit, like low Earth orbit, where the International Space Station and many other satellites live, it could render that region of space incredibly dangerous and effectively unusable for centuries. It would be like building a minefield around our own planet, potentially trapping us here. We aren't there yet, but it's a problem that experts are taking very seriously. It's a reminder that our actions in space have very long-lasting consequences. Now, let's drift back to the experience of being on another world, like the moon. The next terror is another one that sounds almost mundane, but is a huge technical and health challenge: lunar and Martian dust. The soil, or regolith, on the moon isn't like the soil on Earth. It's never been weathered by water or wind. It's essentially microscopic, razor-sharp shards of rock and glass from billions of years of meteorite impacts.
The Apollo astronauts found this lunar dust to be a major problem. It was a fine, gray powder that was incredibly abrasive and clung to everything because of static electricity. It wore down their spacesuit fabric, scratched their visors, and got into all the seals and mechanisms. When they got back inside the lunar module and took their helmets off, they could smell it. They all consistently described the smell as being like spent gunpowder or wet ashes. It was the scent of a world without life, a world of pure, sterile rock. Breathing in this sharp dust would be very bad for your lungs, so keeping it out of the habitat on a long-term moon base is a huge engineering challenge. On Mars, the dust is similar, but with an added chemical twist. We know from our rovers that the Martian soil contains toxic chemicals called perchlorates. So the ever-present red dust on Mars isn't just an abrasive nuisance, it's a toxic hazard that astronauts would have to constantly manage. Let's move from a physical problem to a more abstract psychological one: the communication delay. We are a species built for conversation, for instant feedback. But space has a fundamental speed limit: the speed of light. When the Apollo astronauts were on the moon, the radio delay was about 2.6 seconds for a round trip. It made conversations a little awkward, but it was manageable. But as we venture farther out to Mars, the delay becomes profound.
Depending on where the planets are, a message can take up to 24 minutes to travel one way. That means a simple question and its answer could have a 48-minute gap in between. A real-time conversation is completely impossible. It makes you realize how isolated a crew on Mars would truly be. Every communication would be like a letter sent out into the void with the hope of an eventual reply.
This fundamental isolation leads us to the next point, a concept that's often sensationalized in fiction, but is a very real concern for mission planners: psychological breakdown, or space madness. I think the human mind is the most fragile and complex system we send to space, and putting a small group of people in a tiny box for months or years on end, millions of miles from home, is an incredible psychological pressure cooker. The environment itself is one of extreme monotony. The same walls, the same equipment, the same faces every single day. The view out the window, while beautiful, is largely unchanging. The black of space and the distant red dot of Mars. There are no new sights, no new sounds, no new smells. This sensory deprivation can lead to boredom, depression, and a decline in cognitive function. Then there is the confinement itself. There is no going for a walk to clear your head. There is no privacy. Every moment, every action is shared with your small crew. Minor irritations can fester and grow into major conflicts over time. The wrong mix of personalities could be catastrophic. This is why mission planners spend so much time studying crews in analog environments on Earth, and why crew selection is as much about psychological compatibility as it is about technical skill. And perhaps the most profound psychological factor is the Earth out of view phenomenon. I find this one particularly unsettling to think about. A crew traveling to Mars would, for the first time in history, watch their home planet shrink until it became just another star in the sky. The entire world, everyone you love, every place you've ever been, all contained in a single distant point of light. The psychological impact of that, of truly seeing your complete and total separation from the entire human species, is something we can only guess at.
Now for a related problem, one that doctors have only really begun to understand in the last decade or so. It's called SANS, which stands for Spaceflight Associated Neuroocular Syndrome. It's a fancy name for a mysterious problem with astronauts' vision. Many astronauts who spend a long time in space return to Earth with their eyesight having changed. Their vision often becomes slightly blurrier, a little more farsighted. And when doctors have examined their eyes, they've found physical changes. The back of the eyeball can get a little flattened, the optic nerve can become swollen, and there can be folds in the choroid, a layer at the back of the eye. For some astronauts, these changes are temporary and their vision returns to normal after some time back on Earth. But for others, the changes appear to be long-lasting or even permanent. What's causing it? The leading theory is that it's related to that fluid shift that happens in microgravity, the one that gives astronauts a puffy face. The idea is that the shift of fluids to the head increases the pressure inside the skull, and this pressure then gently pushes on the back of the eyeball, slowly changing its shape and affecting the optic nerve. It's a quiet, slow-moving problem, but a very serious one. If we're going to send people on a 3-year mission to Mars, we need to understand what's happening to their eyes and find a way to prevent it. Our final point in this layer of the iceberg is a more mundane but absolute law of physics: orbital decay. Nothing stays in orbit forever for free. Even in what we think of as the vacuum of space in low Earth orbit, there are still tiny, trace amounts of atmospheric gas. As a satellite or a space station plows through these few stray molecules at 28,000 kilometers per hour, it creates a tiny amount of drag. Over time, this drag causes the spacecraft to lose a little bit of speed, and as it slows down, its altitude drops. The International Space Station, for example, naturally loses about 2 kilometers of altitude every month. To counteract this, it has to be regularly reboosted to a higher orbit. If we were to just abandon it, it would, over the course of a few years, spiral lower and lower until it eventually re-entered the atmosphere and burned up. It's a quiet, constant battle against the faintest wisps of our own atmosphere.
All right, let's take another slow breath and let ourselves sink further down. We've passed through the surface layers of the iceberg, the dangers that are immediate and personal. Now we're entering the murky depths where the concepts get bigger, older, and far more powerful. The terrors on this level aren't things that could go wrong on a mission. They are things that could go wrong for all of us. Cosmic events so large they operate on a scale that is hard to comprehend. Layer 3: the murky depths. Let's start with the most classic cosmic threat, the one you see in disaster movies: impact events. The solar system, especially in its early days, was like a chaotic shooting gallery. And while things have calmed down a lot, it's not completely empty. There are still millions of asteroids and comets orbiting the sun, and sometimes their paths cross ours. We see evidence of this all the time in the form of meteors, those beautiful shooting stars. Most of these are just tiny grains of dust burning up in our atmosphere, but occasionally bigger things hit. In 1908, an object thought to be about 50 meters across exploded over a remote region of Siberia in what's known as the Tunguska event. It flattened over 2,000 square kilometers of forest with the power of a powerful nuclear bomb. And going back further, about 66 million years ago, a much larger asteroid, maybe 10 kilometers wide, slammed into the ocean off the coast of Mexico, creating the Chicxulub crater. That impact is widely believed to have caused the mass extinction event that wiped out the dinosaurs. Now, this isn't something to lose sleep over in a worried way. The chance of a major impact happening in our lifetime is incredibly small, and agencies like NASA have programs dedicated to finding and tracking near-Earth objects to give us a warning. But it's a quiet, humbling reminder that the solar system is still a dynamic place, and our planet has a long history of violent collisions. From a rock coming towards us, let's now consider a threat coming from a distant star, the idea of a nearby supernova. As we've discussed, massive stars end their lives in these spectacular explosions. From a safe distance, they are one of the most beautiful sights in the universe. But what if one happened close by? And in cosmic terms, close by could mean within 50 or 100 light years. If a star went supernova that close to us, the explosion itself wouldn't destroy the Earth. We wouldn't be physically blown away. The real danger is the invisible high-energy radiation. A nearby supernova would blast our solar system with a ferocious wave of X-rays and gamma rays. This intense radiation could be powerful enough to severely damage or even strip away our planet's protective ozone layer. Without the ozone layer, the sun's harmful ultraviolet radiation would reach the surface unimpeded, which could cause a mass extinction event, particularly for life in the oceans. Luckily for us, there are no known stars close enough to us that are set to go supernova anytime soon. The nearest candidate, the red giant star Betelgeuse, is over 600 light-years away, much too far to pose a direct threat. But it's a quiet reminder that our safety on Earth depends not just on our own sun being stable, but on our entire stellar neighborhood being relatively peaceful. Now, let's take the idea of a supernova and turn it up to 11. There is a class of explosion in the universe that is so powerful it makes a supernova look like a tiny firecracker. These are gamma-ray bursts, or GRBs. They are, for a few brief moments, the most luminous and energetic events in the entire universe.
We believe that some GRBs are caused by the collapse of extremely massive, rapidly spinning stars into black holes in an event sometimes called a hypernova. Unlike a normal supernova, which explodes outwards in all directions, a GRB is thought to be a highly focused, tightly beamed jet of pure energy. It's like a cosmic sniper rifle. If a GRB were to happen in our galaxy, and if that beam were pointed directly at Earth, the consequences would be catastrophic, even from thousands of light years away. The intense blast of gamma rays hitting our atmosphere would trigger chemical reactions that would destroy a huge portion of the ozone layer in a matter of seconds. It would be a far more devastating effect than a nearby supernova. Again, the probability of this happening is incredibly low. GRBs are rare, and the beam would have to be aimed perfectly at us. But the sheer, unimaginable power of these events is, to me, a source of profound awe. It's a peek into the most extreme physics the universe has to offer, happening silently in distant galaxies all the time. The next two concepts are less about explosions and more about quiet, wandering intruders. First, the idea of rogue planets and stars. Our solar system is a relatively stable, orderly place, but not all systems are. Sometimes through gravitational interactions in a chaotic young star system, a planet can be ejected, flung out into the darkness of interstellar space. Our galaxy is likely teeming with these rogue planets, dark, cold worlds that are not orbiting any star, just drifting silently through the void. Similarly, stars can be ejected from their home clusters. So the space between the stars is not empty, but is likely populated by these lonely, wandering worlds. The chance of one of these passing through our own solar system is, again,
astronomically small. But if it were to happen, the gravitational effects could be disastrous, disrupting the stable orbits of our own planets. It's a quiet thought, the idea of these dark wanderers drifting unseen through the galactic night. And that leads us to an even bigger and much more mysterious gravitational anomaly. It has a wonderfully ominous name: the Great Attractor. This is not a theory, it's an observation. When we map out the motion of galaxies in our corner of the universe, we see something strange. Everything is moving. Our own Milky Way galaxy, the Andromeda galaxy, and our entire local group of galaxies are all hurtling through space at a speed of over 2 million kilometers per hour. And it's not just us. Our entire supercluster of galaxies, the Laniakea supercluster, seems to be getting pulled towards a single specific point in the sky. This point is called the Great Attractor. It's a massive concentration of mass, millions of light years away, whose gravity is so immense it is pulling in thousands of galaxies from across a huge region of space. The strange part is that when we look in that direction, we can't see what it is. It lies in a region of the sky known as the zone of avoidance, where the plane of our own Milky Way galaxy, with all its thick gas and dust, blocks our view. We know something huge is over there, but we can't get a clear look at it. It's a quiet, cosmic mystery, a reminder that there are colossal structures and forces in our universe that we are only just beginning to map out. Forces that are pulling our entire galaxy towards an unknown destination. Finally, in this layer, we come to a terror that is not a possibility, but a certainty. It's just very, very far away. This is the sun's eventual death. Our star is a wonderfully stable and predictable source of energy, but it will not last forever. In about 5 billion years, the sun will have used up most of the hydrogen fuel in its core. As the fusion process changes, its internal balance will be thrown off. Its core will contract and get hotter, while its outer layers will swell up enormously. The sun will expand into a red giant. It will become hundreds of times larger than it is today, its tenuous outer atmosphere swelling out to engulf the inner planets. First, it will swallow Mercury, then Venus, and then it will reach Earth. Our planet will be vaporized, its oceans boiled away, and its rock absorbed into the fiery plasma of the dying star. It is the ultimate, inevitable end for our world. There is no stopping it. It's a strange thought, isn't it? To know the precise cosmic mechanism of our planet's eventual destruction. To me, this isn't a source of anxiety. The timescale is so immense, so far beyond any human concern, that it becomes a source of calm. It's a powerful reminder of the vast, indifferent cycles of the cosmos. Stars are born, they live, and they die. And planets are just temporary companions along for the ride. It puts our own lives and even our own species' history into a quiet, profound perspective. After its red giant phase, the sun will puff off its outer layers, and its core will collapse into a hot, dense white dwarf, which will then slowly cool for trillions of years. Our solar system will become a cold, dark, silent place. All right, let's take one last deep breath and sink down again into the deepest, darkest, and strangest parts of the iceberg. We are entering the abyss.
Layer 4. The abyss. The concepts in this layer are not about things that could hit us or forces that could pull us. They are ideas from the very edge of physics that question the stability and nature of reality itself. They are, in a way, much scarier, but also much more fascinating. Let's start with what is, in my opinion, the most terrifying concept in all of physics. It's called false vacuum decay. This is a hypothesis that comes from our understanding of quantum field theory. The idea is that our universe might not be in its most stable, lowest energy state. Instead, it might exist in what's called a false vacuum, a state that is stable for now, but not truly, fundamentally stable. Think of it like a boulder resting in a small dip on the side of a huge mountain. It seems stable, but there is a much deeper valley, a much lower energy state far below it. The theory of false vacuum decay suggests that somewhere else in the universe, a tiny bubble of the true vacuum, the state of lowest possible energy, could randomly appear through a process called quantum tunneling. If this were to happen, this bubble of true vacuum would be catastrophic. It would expand outwards in all directions at the speed of light. Inside this bubble, the fundamental laws of physics as we know them would be different. The properties of elementary particles, the forces that govern them, everything could change. As this bubble expanded, it would overwrite our reality, instantly destroying everything it touched, from galaxies and stars down to the atoms themselves. There would be absolutely no warning. Since it travels at the speed of light, we would never see it coming. One moment, our universe exists. The next, it's gone, replaced by a new set of physical laws in a true vacuum state.
Now, I know that idea of false vacuum decay sounds absolutely terrifying. But I should stress, this is at the very edge of theoretical physics. Most physicists believe that if this were a likely scenario, it probably would have happened already in the 13.8 billion years the universe has been around. So, you can relax. It's not something to worry about. It's just a fascinating, mind-bending what if that shows how our understanding of reality is still a work in progress. It's a thought experiment, and as a thought experiment, it's profound. Let's move on from that sudden end to a much, much slower one. This next concept is what most cosmologists consider the most likely ultimate fate of our universe. It's called the heat death of the universe. It's not a fiery death,
but the exact opposite. It is the quiet, final victory of the second law of thermodynamics, the law of entropy, which states that everything in a closed system tends towards disorder. The heat death is the story of the universe slowly running down like an unwinding clock over unimaginable timescales. It begins as stars, one by one, burn through their fuel and die. First the big bright blue stars, then the calmer yellow ones, like our sun, and finally, after trillions of years, even the smallest, dimmest red dwarf stars will flicker out. The universe will become dark, populated only by the dead remnants of stars, white dwarfs, neutron stars, and black holes. After that, over even more incomprehensibly long periods, galaxies themselves will dissolve as the orbits of these dead stars are disrupted. The universe will become a sparse, lonely place. Even the black holes won't last forever. As we discussed, they will slowly evaporate through Hawking radiation. Eventually, after a time so long that the word time loses all meaning, even the largest black holes will be gone. All that will be left is a cold, dark, perfectly uniform soup of stray photons and elementary particles, with no temperature differences, no structure, and no possibility of anything ever happening again. It is the end of time, the end of change. It is the ultimate, eternal quiet. The heat death is a deeply philosophical concept. It suggests that everything we see, everything that has ever happened, is just a temporary, fleeting flash of complexity in a universe whose ultimate destiny is cold, simple emptiness. It's a sobering thought, but like the death of our own sun, the time scale is so immense that it becomes a source of calm perspective rather than anxiety. Now, while the heat death is the most likely scenario, there are a couple of other more dramatic alternative endings for the universe, depending on the true nature of cosmic forces we don't fully understand yet. One is the Big Rip. This idea comes from the mystery of dark energy, the strange force that is causing the expansion of the universe to accelerate. If dark energy is stronger than we think, or if it increases over time, the expansion could become unstoppable. In a Big Rip scenario, the expansion would eventually become so powerful that it would overcome gravity itself. First, it would pull apart clusters of galaxies. Then, it would pull apart individual galaxies as the stars are flung away from each other. As the expansion continued to accelerate, it would become strong enough to overcome the gravity holding solar systems together, and planets would be ripped away from their stars. In the final moments, the expansion would be so violent it would overcome the chemical bonds that hold matter together, and finally, the forces that hold atoms themselves together. The entire universe, every star, every planet, every single atom would be torn to shreds. The opposite scenario is the Big Crunch. This would happen if the force of gravity is ultimately stronger than the push of dark energy. In this case, the expansion of the universe would eventually slow down, stop, and then reverse. The universe would begin to contract, with galaxies rushing towards each other instead of away. It would be like watching the Big Bang happen in reverse, with everything collapsing back into a single, incredibly hot, incredibly dense point, just like the one where it all began.
Whether the universe ends in a cold fade, a violent rip, or a fiery crunch depends on a delicate cosmic balance that we are still trying to measure. For now, the evidence points towards the long, slow, quiet fade of the heat death. Let's now turn from the end of the universe itself to a more personal, biological question. This is another potential solution to the Fermi paradox, which we talked about before, the question of where is everybody? This idea is called the Great Filter. I find this one of the most compelling and unsettling ideas in all of science. The Great Filter theory suggests that there is some step, some barrier in the development of life from a simple molecule to a galaxy-spanning civilization that is so incredibly difficult to overcome that almost no species ever makes it past. This filter could be anything. We don't know what it is. And more importantly, we don't know if we, humanity, are already past it, or if it is still waiting for us in our future. For example, maybe the Great Filter is the very beginning of life itself. Perhaps the leap from non-living chemistry to the first self-replicating cell is so astronomically improbable that it has happened only once on our planet. In this case, we would be the first and only life in the galaxy. We are past the filter. This is a lonely but very hopeful scenario. Or maybe simple life is common, but the filter is the leap to complex life, like plants and animals. Or maybe complex life is common, but the filter is the development of intelligence. Or maybe intelligence is common, but the filter is developing technology that allows a civilization to leave its home planet. The scary possibility is that the Great Filter is still ahead of us. Maybe every intelligent civilization eventually discovers a technology like nuclear weapons or artificial intelligence that inevitably leads to its own self-destruction. In this scenario, the silence of the sky is not because we are first, but because we are next.
Let's move on to another theoretical concept, this one from the world of particle physics. It's the idea of strangelets. This requires a little bit of explaining. Protons and neutrons, the particles that make up the nucleus of every atom, are themselves made of smaller particles called quarks. We have different flavors of quarks, primarily up and down quarks, but there are other, heavier flavors, like the strange quark. The theory goes that under extreme pressure, like in the core of a neutron star, the up and down quarks could be squeezed together to form a more stable kind of matter made of up, down, and strange quarks. This is called strange matter. And here's the terrifying part. It's hypothesized that strange matter might be the most stable form of matter in the universe. A tiny, stable lump of strange matter is called a strangelet. If this hypothesis is true, and if a strangelet were to ever come into contact with normal matter, like an atom of hydrogen or iron, it could trigger a chain reaction. The normal matter would be instantly converted into more strange matter. If a microscopic strangelet were to hit the Earth, it could potentially convert our entire planet from the core outwards into a dense, hot ball of strange matter. It's a bit like the fictional Ice Nine from Kurt Vonnegut's novel Cat's Cradle, a seed of a more stable state that converts everything it touches. Now, I should say, this is highly speculative. We have never observed strange matter, and there are good reasons to think it might not be stable in the way this theory suggests. but as a concept, it's a truly strange one.
And now, for what I think is the single weirdest and most mind-bending idea on this layer of the iceberg. It's a bizarre cosmological thought experiment called Boltzmann brains. This one's a real head-scratcher, so just let the strangeness of it wash over you. It comes from thinking about the heat death of the universe. Remember that final state? A cold, dark, uniform soup of particles in a state of maximum entropy or disorder. Well, if the universe lasts for a truly infinite or near infinite amount of time, then even in that state of perfect disorder, random quantum fluctuations will still happen. And if you wait long enough, absolutely anything that is physically possible will eventually happen. In fact, it will happen an infinite number of times. The physicist Ludwig Boltzmann applied this idea to consciousness. The thought experiment goes like this. In an infinitely old universe, which is more statistically likely for a massive, low-entropy, highly ordered system like our entire observable universe to spontaneously fluctuate into existence as it did in the Big Bang, or for a much smaller, simpler system like a single self-aware human brain, complete with false memories of a life it never lived, to spontaneously fluctuate into existence for just a moment before dissolving back into chaos. The unnerving answer is that it is vastly, incomprehensibly more likely for a single Boltzmann brain to pop into existence than for a whole universe like ours. This leads to a strange philosophical paradox. If this is true, why do we find ourselves in this vast, ordered universe? How can we be sure that we are not, in fact, just a momentary Boltzmann brain experiencing the fleeting illusion of a past and a universe that isn't really there? It's not a theory meant to be taken literally, but a philosophical puzzle that challenges our most basic assumptions about our own existence and observations. It's a deep, weird, and wonderfully unsettling idea to ponder.
Layer 5. The Crush Depths. Let's begin with a concept that is not a theory, but a simple, observable fact, yet one whose implications are truly profound. It's the idea of the unobservable universe. We know the universe began about 13.8 billion years ago in the Big Bang. This means that the absolute farthest we can possibly see is 13.8 billion light years in any direction. Light from any farther away than that simply has not had enough time to reach us yet. This sphere around us with a radius of about 13.8 billion light years is what we call the observable universe. But there is no reason to think that the universe just stops at the edge of what we can see. The universe beyond our horizon is likely just more of the same. More galaxies, more clusters, more voids. And because the universe is not only vast, but also expanding, and that expansion is accelerating, there are vast regions of space whose light will never ever be able to reach us. Space itself is expanding faster than the light from those distant galaxies can travel towards us. This means that we are fundamentally and permanently cut off from seeing most of reality. We live inside a small, finite bubble of observation. And the vast majority of the universe lies outside this bubble, forever beyond our reach. We can never know how big the entire universe is,
or if it is infinite. We are like sailors on a small raft in the middle of an ocean, able to see only to the horizon, with no way of ever knowing if the ocean goes on forever. It's a deep and fundamental form of cosmic isolation.
From a physical boundary, let's move to a philosophical one. This next idea has become more popular in recent years, a favorite topic of late-night conversations. It's the simulation hypothesis. This is the philosophical argument that our reality, everything we experience, might be an incredibly advanced computer simulation. The idea, in its modern form, goes something like this. If you assume that any civilization advanced enough to create a completely realistic simulated universe with conscious beings inside it, would likely create many such simulations, then it becomes a simple matter of statistics. There would be billions upon billions of simulated universes and only one base reality. Therefore, it is statistically far more likely that we are living in one of the simulations than in the one original physical universe. It's a fascinating argument, and it's one that is, at least for now, completely unfalsifiable. There is no experiment we can perform, no observation we can make that could definitively prove we are not in a simulation. Any evidence we found could simply be part of the simulation's code. The terror here is a quiet, existential one. It's the idea that our reality might not be fundamental, that our lives, our feelings, our entire universe might be, in essence, a piece of software running on some unimaginable computer in another, higher reality. It's a thought that can feel a bit like the ground beneath your feet has suddenly become less solid. It's not a scientific theory, but a philosophical puzzle that playfully pulls at the loose threads of what we consider to be real. It's the ultimate what if.
Now, let's drift from the idea that our reality might be a program to a feeling that is perhaps even more profound. This isn't a scientific theory, but a philosophical one, often explored in fiction, especially by writers like H.P. Lovecraft. This is the concept of cosmic horror, or the terror of the indifferent universe. When we normally think of horror, we think of things that are actively hostile to us, monsters, villains, things that have a specific malicious intent. But cosmic horror is different. The terror in this idea is not that the universe hates us, it's that the universe doesn't even know or care that we exist. It is completely, totally, and profoundly indifferent to us. Our hopes, our dreams, our morality, our consciousness, our entire concept of meaning, these are all deeply human things. In the grand scheme of the cosmos, they are likely just a tiny, accidental, and temporary chemical reaction happening on a speck of dust orbiting an average star in a forgotten corner of an ordinary galaxy. The universe is billions of years old. It is filled with forces like black holes and gamma ray bursts that are so powerful they defy our comprehension. In the face of that immense, ancient, and unthinking reality, our existence is a fleeting statistical blip. The horror, then, is the confrontation with our own ultimate insignificance.
It's the realization that our lives have no inherent cosmic purpose. The universe was not made for us. We are just a brief, complex pattern that has temporarily emerged from the chaos and will one day dissolve back into it. To me, this isn't a depressing thought. It's a liberating one. If there is no pre-written cosmic meaning, then we are free to create our own. It inspires a deep sense of humility and a greater appreciation for the small, warm bubble of meaning and connection we create for ourselves in this vast, silent, and indifferent space.
From the terror of cosmic indifference, let's turn inward to the terror of ultimate, inescapable loneliness. This is a very old philosophical idea called solipsism. It's a simple concept, but one that is impossible to disprove. Solipsism is the idea that the only thing you can be truly sure exists is your own mind, your own consciousness. Think about it. You experience the outside world through your senses. You see a chair, you touch it, you feel its solidity. But all of that is just sensory data being processed by your brain. You can't prove that the chair exists independently of your perception of it. And this applies to other people too. You can talk to another person, you can hear their thoughts and feel their emotions, but you can never truly know that they have an inner conscious experience just like you do. You can't prove that they aren't just an incredibly sophisticated automaton, a philosophical zombie, perfectly mimicking the behavior of a conscious being without any actual awareness inside. Now let's apply this to space. Imagine you are an astronaut on a long journey to Mars with a small crew. Solipsism is the ultimate isolation. It's the quiet, unnerving thought that not only are you millions of miles from home, but you might be the only truly conscious entity in the entire universe. That your crewmates, mission control, everyone back on Earth might just be part of a complex dream that your own mind is generating. Again, this isn't a scientific theory to be believed. It's a philosophical puzzle, a thought experiment that explores the limits of knowledge. It's a journey into the strange nature of consciousness itself, a quiet reminder that our own internal world is the only one we can ever truly, directly know. It is the final, deepest, most personal kind of solitude.
And now, for our final point, the very bottom of the iceberg. We will ascend from the depths of philosophy back into the world of cosmology, but with a final, unsettling twist. This is the anthropic principle's dark corollary. First, let's talk about the anthropic principle itself. It's a way of dealing with the observation that our universe seems to be strangely, almost suspiciously fine-tuned for life. The fundamental constants of physics, the strength of gravity, the mass of a proton, the energy of the vacuum, all seem to be set to values within a very narrow range that allows for stars, planets, chemistry, and ultimately us to exist. If any of these values were just slightly different, the universe would be a sterile, empty place. Why is it so perfect? The anthropic principle offers a simple, if slightly unsatisfying, answer. If the universe weren't like this, we wouldn't be here to wonder about it. Our very existence as observers selects for a universe that is capable of producing observers. It's a form of selection bias. But this has
a quiet, dark corollary, a worrying implication. It suggests that our observation of a stable, long-lived, life-friendly universe might be incredibly misleading. We might think that this is what a typical universe is like, but we have a sample size of exactly one. What if, for every stable universe like ours that lasts long enough for intelligent life to evolve and ask these questions, there are trillions upon trillions of other universes that are far more chaotic and hostile? Universes that flicker into existence and immediately collapse. Universes where the laws of physics are a tangled mess that doesn't allow for any stable structures to form. The dark corollary is the idea that our existence might be predicated on living in an extraordinarily rare, perhaps fragile, bubble of stability. We are, by necessity, blind to the true, average nature of reality, which might be far more chaotic than we can imagine. We think the universe is calm and orderly because we could only have arisen in a calm and orderly one. It's the final, unsettling thought that our perception of a safe cosmos might be the ultimate survival bias.
And with that thought, we have reached the bottom of our iceberg. We have taken a long, slow descent from the immediate physical dangers of space travel, down through the subtle threats of the cosmic environment, into the vast and existential threats of astronomical events, and finally into the deepest, most profound philosophical questions about the nature of reality itself. Let's now begin our gentle ascent back up to the surface. Let these vast, strange, and awesome ideas slowly recede. Let the concepts of false vacuums and Boltzmann brains dissolve back into the quiet of the night. Let the immense distances and timescales settle in your mind, not as a source of fear, but as a source of deep and profound calm. The purpose of this journey wasn't to create anxiety, but to provide perspective. The universe is ancient, vast, and filled with forces that are beyond our comprehension. Our existence within it is a remarkable and perhaps incredibly rare phenomenon. We live on a tiny, fragile world, protected by a thin blanket of air and an invisible magnetic shield, in a quiet, stable corner of a vast galaxy. Contemplating these immense and sometimes terrifying ideas can have a strangely peaceful effect. It shows us that the universe is not a story about us, but we are a small but beautiful part of its story. It can make our own daily worries, our own anxieties, feel as distant and as small as the light from another galaxy. So as you continue to drift off tonight, let your mind be quiet. You have journeyed through the deepest and strangest ideas the cosmos has to offer. Now it is time to return home, to the simple, peaceful comfort of a safe place to rest. Let the scale of the universe be a soothing lullaby, a quiet reminder of the peace that can be found in the vast, silent dark. Sweet dreams.